Welcome back to this next session of the SWAYAM course. So this is essentially going to be a lecture which picks up from where we left last time. So last time, if you recall, we continued the discussion on polymers, and essentially the numbers that were given in a table like this was used to deduce and also elicit some student response. And students rather independently used their data devices, for instance, in order to look at the differences between, let us say, low density polyethylene and high density polyethylene. And at some level, they gain an appreciation for the fact that despite the very marginal improvement in the density, basically just 3%, there is a dramatic difference in mechanical properties in particular. And they also compared this, for instance, polyethylene with polytetrafluoroethylene, which is essentially a situation wherein you remove the hydrogens and then replace it with fluorine. And as a consequence, they were able to sort of rationalize using the chemistries the vastly different specific gravity, for obvious reasons, to do with the fact that fluorine is much heavier than hydrogen, and also the CF bond being much more dipolar. You expect a great more degree of secondary forces operational in the case of, let us say, polytetrafluoroethylene vis-a-vis polyethylene. So these were the distinctions that were made, and students also got to appreciate the distinctions between, let us say, tensile modulus vis-a-vis tensile strength. There is a clear distinction to be made. And in the class, we actually also talked about the difference between what is called as the elastic limit and the proportionality limit. It is in fact something that was discussed during our graphing exercises also, which was undertaken during this particular course. And they also were able to rationalize the elongation differences and yield strength. The most dramatic distinction being, let us say, as you go from low density to high density polyethylene, they appreciated the fact that there is higher degree of crystallinity, and the higher degree of crystallinity meant that the polymer was being packed following the fringed micelle model in a rather regular manner in an ocean amorphous region. So if you were to pull this polymer, you would have a possibility of getting much more significant elongation when compared to a bunch of, let us say, interconnected polymers that are basically together. There is really no reason to believe that this would have higher elongation than this, because at the very least you could actually spread it out in this particular manner. However, we also noticed that the fringed micelle model, as represented by this diagram, let me show that for reinforcement of this particular lesson. So this is the fringed micelle model, wherein you have crystallinity, for instance, and there are these crystalline chains that are there in an amorphous bed. And this is the very famous fringed micelle model, and it turns out that this fringed micelle model is widely used in order to rationalize the emergent morphologies that exist in the case of polymers. And there are rather interesting consequences to thinking about this. In the class, for instance, we had some interesting thought experiments wherein we asked the following question. If you had to vary this interchain distance, for instance, what would be the tricks that you could use? And there were some rather innovative ideas that came from this class, wherein they said, what about constrained solidification? And that's a good answer. It is only that we do not understand constrained solidification well enough, but there were other solutions provided. For instance, how about intercalating some small molecules inside so that they diffuse in and they separate it out? So the concentration of the small molecules would determine the interchain distances and so on. And that was also a solution that the students came up by and large independently by their own thinking. So students are actually quite capable of design thinking. And this has to do with the fact that they are developmentally fairly high up in the Piaget's developmental cycle, or in the developmental ladder. They basically come to you with the ability to do abstract thinking, concrete formal thinking, and at the same time use concepts from one domain to another domain, and they are certainly capable of extrapolating ideas. So here in the class, when a question like that was given, what would you do if you had to play with this? They came up with solutions on their own. We didn't have to give the solutions. They more or less came with came up with the solutions by wrestling with the possibilities that might actually exist. And that's a good way, by the way, to teach, because of the fact that when you elicit response, there is an active participation from the student. So this is by and large where we left off, and I in fact showed a picture which was, I think, very essential from the point of view of understanding the mechanical response, particularly, let us say, the tensile stress test associated with polymers. So this is sort of what we see. So you will have, let us say, a crystallite here, another crystalline region here, and notice that these crystalline regions were sitting next to one another, connected by these chains, and notice that these chains are not necessarily aligned, right? So when you apply strain, when you apply stress, the strain is first going to occur here. All right, here is where you would actually find all of this, the equivalent of necking, so to speak, wherein you have these chains that are pulled apart. The crystalline regions are actually pulled apart as a consequence, and as a consequence you would also have extraordinary elongation. Now if this is a very, very crystalline region, notice that the amount of material that is available from this crystalline region is very significant, and that is the reason why most crystalline polymers, for instance, high density polymers, tend to have an elongation that is much larger than the low density analogs. Okay, that is because if you look at this particular figure, you will find where this is actually coming from. Originally it was the amorphous region, but it intercalates and it actually intersperses, it is continuous with the crystalline region, and now if you were to pull it further, you would be actually drawing more and more material from here. You understand? So that is the reason why this elongation was something like 1200% for HDPE, while it was only about 600% max for LDPE. And which of the two was crystalline, by the way? Do you recall? More crystalline? HDPE was more crystalline, way more crystalline. And with increase in crystallinity, what happened to the tensile modulus? Did it increase or decrease? It increased, right? So the tensile modulus also increased. So crystallinity is indeed one of the very nice parameters by which you can vary a vast number of properties, including tensile modulus. Okay, we saw in this particular class, for instance, how you could play with that for improving or changing the optical index, improving or changing the way in which plastics respond to polarized light. And it turns out that you can also play with it for changing the hardness of the material. Alright, so that is certainly one take home, rather important take home, that I would like you to have from this particular set of chapters. And also another thing that I wanted to show you, and this is something that we discussed in the class. It is not at all surprising, isn't it? Because if you took a sheet of paper and if you did this, you would clearly see regions where then there is substantial strain, right? So you would actually find that it's not going to be a uniform stress distribution. In practice, when you do this, you will actually expect a great degree of striations to actually occur, regions wherein there is a lot of concentration of stress, and as a consequence, a substantial amount of strain, and they can open up to give rise to micro voids. And this is again perfectly analogous to what you would actually expect even in a metal, let us say very close to its melting point. You apply stress, and then you would have stress distributions that can actually result in micro voids and so on. And notice that this region is essentially where necking is happening. And if you notice this, at the tip of this there is necking happening. And that is the reason why if you actually looked at crystallinity here versus crystallinity here, you would expect more alignment and crystallinity here. So that distinction, by the way, gives you a lot of information about the mechanism involved in crazing. And this particular phenomena was called crazing. So you have these bridges here, okay, so these are called fibrillar bridges. You have a lot of stress and that results in alignment here, okay. There is progressively higher and higher amount of alignment here. So, but there is bridging, there is no discontinuity yet until discontinuity sets in. When does discontinuity set in? When this snaps. Typically this will snap before this does, and this will snap before this does. So there is a propagation of this. This is somewhat analogous to crack propagation in a ceramic. Okay, this region opens up, then this opens up, and so on. Alright. Now think about it. If I had more and more bridges, would it be easy to open this up? No, it wouldn't be easy, right? So if I had alignment, for example, along this, then it would actually mean that I have lots and lots of bridges. I would have lots and lots of fibrillar bridges, and that would inevitably mean to say that this would be a system that would be resistant to cracking, it would be resistant to crazing. So you can make polymers as a consequence that are resistant to crazing. Okay, so in fact, what would be the strategy to make a craze resistant plastic? Have lots of fibrillar bridges, and that is equivalent to saying have lots and lots of alignment. So when you are developing a process to make this particular polymer, it's a good idea for you to actually have alignment. Alright, so this is by and large what we discussed last class, and we arrived at it deductively. Alright, so that is by and large how we approach this. And in terms of pedagogy, in the last class we discussed a few things. Primarily we talked about things like cognitive development of the student vis-a-vis student development. Okay, so cognitive development primarily intends to address the intellectual needs of the student, which can be vastly different between any two students. You know, one student might have need for analytic thinking, and we discussed that. Some other students might have need for creative thinking, and we discussed that. And we discussed that a person who is very creative need not be very interested in analytic thinking, and vice versa. It's a possibility. That's why you will find some people who might be fantastic problem solvers in one area may not necessarily come up with a new idea between areas. And that has to do with the fact that different people think differently. Alright, some people may be able to actually just zoom out and come up with a new idea, but they are not necessarily going to do the analytic thinking that is necessary for a full academic discourse of it, for instance. And ideally in a classroom like the one that we have, it would be helpful to have a mishmash of analytic versus creative thinking, and to sort of acknowledge this, that there is a cognitive need for development of the analytic part of the brain, but also the creative side of the brain. And that is actually very helpful for students in this day and age, wherein they are expected to come up with innovative solutions, new solutions. This century is different from any other century in the sense that students are expected to think out of the box, and it is a norm today. Okay, and this was distinguished from what is called as student development, and there were some premise that are associated with student development. Let me show that. So this was what I showed. In college and university education, it refers to the integration of academic learning with students' personal and individual growth. The aim is to help the student achieve holistic development focused on improved analytic skills coupled with values, nurturing skills, and a general movement towards lifelong learning. So all of us, I think, at some level as educators become tremendously modest when we realize that we will, number one, never be able to teach all that we want to teach. There is really no scope or time for that. And number three, we will never be able to teach everything that is necessary and relevant for the student's life. Okay, so the best thing to, as a consequence, focus on is to set up a schema for them, so that they will be prepared for lifelong learning. If they had to learn on their own, they would be able to do that throughout their life. So setting up that schema, that mechanism in place, is much more valuable to students than just, let us say, exploration of content, because there is an amazing amount of content there. There's no way in which we can cover all of that, but we can scaffold it suitably, especially set up a schema for thinking, asking the right questions, a Socratic inquiry of the same, and so on and so on. Okay, and then the other thing that we discussed was some of these principles. Now these are the axiomatic foundations of the student development movement. The first one being that each student is a unique individual. So it is at some level ethically wrong to compare two students with respect to one another, and this results in great many paradoxes. The obvious paradox being that we very often use a norm referenced evaluative mechanism. So typically in my courses, for instance, I try to use a combination of ipsative evaluative mechanism and criterion referenced evaluative mechanism in order to by and large overcome that. And in many cases it actually becomes consistent with the norm referenced one also, especially if it's a very large class. But if it's a small class, you need to sort of balance it out with what is called as the ipsative mechanism, alright, the ipsative evaluation, and the criteria referenced one, referenced evaluation. So in the ipsative evaluation mechanism, you sort of ask, where was the student before entering the class, and through the class and the work that she or he is putting in the class, is she actually growing, and sort of giving credit for the work that they put in and the growth that they have taken responsibility for. So this is of course going to be different from criteria referenced one, wherein I sort of say, okay, as part of this particular course, I expect my students to be able to do A, B, C, D. At the end of this, let's say this lecture, I expect them to do 1, 2, 3. At the end of this course, I expect them to do, bullet 1, bullet 2, bullet 3. So you can have some combination of ipsative and criteria referenced evaluation, and in my perspective, that is the only way to sort of be consistent with this idea. And this is an axiomatic idea, okay, really, for all practical purposes, that is treating each student as if they are an individual, a unique individual, treat them distinctly based on their own personality, and that is true for any human being for that matter. The second is that the student's environment needs to be deployed for their education. I mean, that is precisely one of the reasons why we actually started out this course by talking about the importance of ambience. And I must agree that even in IIT Madras, for instance, it's very difficult to find classrooms like this. And progressively over the next 10 or 20 years, we hope that we have classrooms wherein Harkness tables, quote unquote, are enabled, Socratic discussions are enabled. It is extremely challenging because this requires a complete modification of space, and very often there might also be space constraints. So Professor Pratap Haridas, for instance, is now undertaking a project with the materials department wherein we are setting up another similar space to basically ask the question, how is it that you can achieve something along these lines wherein there can be appropriate level of interaction that is enabled between two or more students in the context of active cooperative learning with the constraints that exist in our traditional classrooms. So there is some data being gathered there and some exercises being done there and so on. And hopefully as an outcome of that, we will be able to communicate in a forum like this. In a while, we may be able to provide a solution for some of the challenges you face in your own respective classrooms, wherein there is a space constraint and there is a very traditional setting wherein the assumption is that there is a monologue as opposed to dialogue and so on. And the last thing is rather critical, because you are sort of saying that I respect my student and hence I give him or her the personal responsibility for her own growth. So this is at some level saying that, look here, my responsibility is to provide the setting, the environment, ask the right questions, set the right criteria, for instance, but at the same time say that the student is a unique individual and as a consequence will need to take personal responsibility for their growth. And this has been a very interesting movement around the world because I have seen a lot of positive outcomes associated with this. Alright, and I have asked this question, which is relevant for university educators in my opinion. The question being that, what are the constraints that we envision within our campuses which prevent student development? And by the way, this could also be something that is systemic. For instance, it could be an academic requirement, a non-academic requirement to do with the academic atmosphere, the non-academic atmosphere. The whole range of things could possibly go into this bunch of possible developmental challenges that the students face, especially because students are unique. And setting up system that is optimized for every individual will just be not possible. So very often we come up with a compromise, but then do we understand that at least? And with that knowledge, are we able to sort of think about student development in a very, very fundamentally robust manner? Is a question that I think students and teachers should think about. I feel all students should also think about this. I mean, today more than ever before, we probably have students that are empowered like no other generation because they have information, they have data, they have access to information, more information than they can ever process, more information than we can ever process. So the question then becomes, how do you take charge of this resource, the set of resources that are available? What would be the most optimal approach for the same? And how can you ensure personal human development in the middle of all of this? And I think that is a very fundamental problem. And I had asked you to sort of follow up. If you are interested in problems of this sort or literature of this sort, you can look up primarily these three. So these will be the key words associated with the student development associated foundational theories. Okay. So the Kohlberg's theory, the Kohl's learning theory, and the challenge support balance theory. And I particularly like challenge support balance theory because it goes hand in hand with something I am going to discuss today called the flow. And it's a very powerful idea and we will be discussing that in a while. So the challenge support balance theory basically says that it is not sufficient to just support the student, you should challenge the student. The student should be able to exercise their intellect and feel challenged. But at the same time, if the challenge becomes too much, the student might get overwhelmed. So you need to balance out the challenge and support so that the student is not giving up on learning. Okay, so that is by and large what we spoke about last time. We also spoke about the distinction between extrinsic motivation and intrinsic motivation, and also something called the over justification effect. So let me write that down because it's an important idea. And we discussed this in the context of intrinsic and extrinsic motivation. And we realized that intrinsic motivation is sort of that which governs the behavior of the student regardless of the extrinsic factors, right? And extrinsic motivators, on the other hand, sort of governs behavior primarily because of factors other than that which comes from the student. That can include things like, stipend, salaries, status in the society, parental approval, and the numerous other things. But we also learnt that extrinsic motivation is unsustainable in the really long run. You cannot ask a person to do something that they don't like or they are not interested in, for instance, and provide extrinsic motivation to them. They may do it for some time, they may not be able to do it lifelong. Intrinsic motivation, on the other hand, can be something that is very sustainable. The problem though is increasingly there can be a culture wherein we reward a person extrinsically so that we hope that there is some motivation that is created for the action. But when you reward somebody who is already intrinsically motivated, especially in unreasonable manner, the person basically shifts from intrinsic motivation to extrinsic motivation. And what might be intrinsically present might get lost. Okay, so there is that real danger. And one of the questions I asked in the last class is, how do you do justice in a classroom then, wherein you might have some students who are very, very intrinsically motivated, some students who just cannot be intrinsically motivated, and then everybody in between. How do you still manage and go around this? Because I feel that there is a real paradox here. Nonetheless, there is another data. The data is, if a person is not at all motivated, you can provide extrinsic motivation, then chase mastery, get the student to be a master, get mastery, and at that point, there can be intrinsic motivation. So there can be a translation to intrinsic motivation. So that is one thing that is rather interesting. Okay. So with that, we will come to the pedagogical topic that we have supposed to cover today, and that is called Mihaly's flow, or Csikszentmihalyi's flow, after the Czech scientist Csikszentmihalyi. Okay. So Csikszentmihalyi found this rather interesting graph. Okay. So I hope you are able to see it from there. Let me zoom it out. I got it from the wiki article on Mihaly actually, and it's available in his book, in his publications. They took it from there, in fact. So Csikszentmihalyi was very interested in not just students but workers of all sorts, And what Csikszentmihalyi did was, he, through his research, was able to come up with this rather interesting chart. Okay, so here you have skill level. Okay, so for a particular task, what is the skill level? So a person may have low skill level or middle level skill level or high skill level, and then you could have the task at hand which has different levels of challenges. For instance, it could be a very highly challenging task, or it could be medium challenge or very low level challenge. Now, if the skill level is low and the challenge level is very low, nobody cares. The student doesn't care. The worker doesn't care. They can't do anything about the challenge, and the challenge is not challenging enough. So there is absolutely nothing they will do about it. The work will not get done. Okay. On the other hand, let us say that you have a high skill level, a medium level skill level, but the challenge is very low level. It's a very moderate level of challenge for somebody who has a middle level skill level, not necessarily high, but middle level. So this person can do more than this in the same time, and as a consequence, the person gets bored. They will give up eventually. So there's definitely a lot of productivity. There's not a lot of productivity here. All right. If there is a very high level of skill, but very low level of challenge, then the person is just relaxed. The person will do something, will relax, will not do much. So again, you are not using the person effectively there. Certainly the skill is not used effectively. Now what happens when the challenge level is, let us say, somewhere in middle, alright, so it is not super easy, but the person is highly skilled, the person says, I'll do it, no problem. It is not that I am bored, it is not that I am relaxed, I have to still work, but I feel in control, it's not overwhelming. But now what happens, you keep the same skill level, high skill level, and also challenge the person. The person will be in flow, because the person has to draw everything in their skill set to perform that. Okay, so the person will be in flow, they will be having razor sharp focus. What comes out will typically be very high quality work. Alright, now if the skill level is middle and the challenge level is high, then the person might be interested, but there is no guarantee that the person will get much done. Because the task that is required here is actually of a fairly highly skilled person, and the person might be here. But the person can upskill and be in flow. That is a possibility. If the person is here, the person is aroused, and then the person say, okay, what should I do so that I can solve this problem? They upskill themselves, they go in this direction, and then the person is in flow. They will enjoy the work and they will turn in high quality work. So our job should be to sort of push people in this direction and provide problems in this direction. So the challenge level of the problem should be moving in this direction and in this direction. At any given point of time, we should make sure that the student, or we for instance, should be operating in a flow. Then we are actually having a truly optimal system. If you are not operating here, then you are in trouble. Now for instance, we are dealing with somebody who has very low skills, but the challenge is at a middle level. The person will worry. They won't give up, but they will worry. If it is a very high level, the person will be anxious. The person won't be able to sleep at night. That's a problem too. Nothing will come out of it, and the person is not moving in this direction. So the key is at any given point of time, matching the skill with the task. Matching the skill with the problem so that we by and large use this idea of flow. So let's just read what Csikszentmihalyi has written in his book. He said, I have paraphrased it of course. When people achieve a state of concentration wherein nothing else matters and they are in zone or in the groove, they are in an optimal state of intrinsic motivation. So this is really the possible way of providing intrinsic motivation. So you ensure that the person is in flow. So this is a very major key. So why is it that some people are not intrinsically motivated? Maybe they are not in the zone, they are not in the groove. Most likely they are not in the groove, not in the zone, and hence they are not in an optimal state of intrinsic motivation. And hence now if they are in the groove or in the zone, they are probably the happiest, because they are intrinsically motivated, they are very happy. Okay, and this has profound implications on creativity and has a place in learning settings. So a person who is very happy and is in flow, they will zoom out, will come up with a flurry of possibilities. They will solve this problem and generate new problems and solutions for that. So you're dealing with a person who is in flow. So really, engineering a learning setting has to do with making sure that the persons involved are by and large operating in flow. And it's easier said than done. Okay. So for those who are interested in learning more, I welcome you to read Csikszentmihalyi's books, which are very widely read by the way, on flow. It's a concept that has been around for quite a few decades now, and hence is actually accepted as a real way to engineer learning, teaching settings, and also to engineer workplace settings, workplace challenges, to manage workplace projects, and so on and so on. Okay. So how may you approach your teaching learning activities so that you may optimize flow options for yourself? And this is a bunch of students. I would like to ask you this question. Okay, so you are all signed up for one program or the other. Are you in flow? It's okay if you are not in flow. Most of us are not in flow most of the time. But what would you do, number one, to realize that there may be a need for self-regulation? It is making you responsible for your own learning and your own work at hand. And what may you do, given your life situations right now, to make sure that you are in flow? That's the question. Okay, so can you discuss with one another, please? You understand the concept? You understand the concept, right, of flow? So I'll show you the picture again, the chart, because that should help you. It's very nice, no? It's like phase diagram in material science, right? Correct? Like these are like the degrees of freedom, and this is like a phase diagram, right? You follow the question, Naveen? The question is, what would you do to ensure that you are in a state of flow? Because you understand that flow is helpful, right? So, what did you tell him?
We are asking in our situation.
In your own situation.
And we are doing some project work. So we will face some challenges. So if we are experimental, we will face some challenges. So just first analyze what is your challenge, and you will require some set of skill set to solve that. So if you know that you don't have enough skill set for solving the problem, first work on
the skills. So yes. So identify where the gap is. Why is it that what is it that the job requires? What is it that the project requires? And identify the skills. Work on developing the skills so that ideally you are having a high level of skill in that area, and then you challenge yourself appropriately so that there is an appropriately high level of problem solving that is demonstrated and executed by you. So that's what you are saying. So very good. So you need to work on skills basically. That's one thing you are saying. Wonderful. Very nice. What did you realize from this? So skill level, now you are moving in this direction. Oh, fantastic. Very nice. That's the good direction. That's good. Very good. But as he pointed out, if you identify what are the skills that you need to really focus on, then it becomes easy for you to sort of upskill yourself there. So you can move there, and the level of challenge that you take up is also appropriately high. So you enjoy the activity. So you experience flow. So what comes out of you would be much better than what would come out without this kind of a design. That's what is the power of Csikszentmihalyi's flow idea. So it's a very powerful idea, very helpful idea, no question about it. Yes, Bodhi, what are your thoughts? What did you tell Malik?
Just find out what are the skills required.
So what Malik says is the opposite, no? Sometimes you get into a project and you can first of all look at the challenge level that the project presents, right? And then accordingly upskill yourself. So that's what he's saying. So he says, let us start with the end goal in mind. The end goal requires a certain level of skill. So you map it out, you decide it, and then focus on that and develop that skill. That's what he's saying. That's a very efficient way of going about doing it, right? So you say, this is the task, this is the problem I have. So I need skill at this level. Okay, I need skill 1 this level, skill 2 this level, skill 3 this level, and I achieve those or more. So suppose the level of skill in a 1 to 5 point scale, you require skill at 3 for this particular project, get to 4 or 3.5 at least, so that you are in the zone, in the groove. Okay, all right, good. All right, what did you find? Yeah, so you are putting it the other way around. So Malik starts with the project first approach. What is the project I have? So what are the skills that are required? Okay, and then I'll chase those skills at that level. Alright, what you are saying is, these are my skills, so this is the project I will choose. But I think you have to mix the two, right? You have to come up with a superposition of the two, a resonance hybrid of the two. Okay, because there may be some cases wherein you say, okay, this is my skill level, so this is the project I will do. But if you never chose upskilling, then the skill will never go up. You will continue doing project at one level, not necessarily take up projects beyond that level, right? So it's very valuable as a consequence to think about a combination of projects. One project wherein you are still productive with your current skill levels, but then take up something that requires upskilling and deliver there. And if you keep doing it continuously, you will obviously move up like this. Hopefully you will never be here, and you will sort of push yourself in this direction, or you may push yourself in this direction. This is a good zone because you are either in control or flow. So you have skills, then the question is, what is the project can I do? What's the project I do? You will have control over it. So you will feel in control, but you are still not in flow. So you may have to sort of choose projects that are sufficiently challenging as well. Okay, so this is a very interesting project ideation tool, no, project design tool, right? Without this, you may not really know at what level you should pitch your project, but with this, you will be able to sort of ideate about your projects, your project modalities, the skill composition that is required, the work element composition that is required, and so on. Correct? Hannah Malik? Good. Wonderful. The next thing is, how would you personalize advice to students so as to nudge them towards flow? Remember, this has implications to their development and creative output. So you are a teacher, and how will you use this data, this chart, okay, to scaffold your students? So put yourself in the shoes of a teacher who is responsible for the development of somebody, okay, who may not have as much experience as you have, but has come to you because you have some experience. So how could you use this to help her or him? You understand the question? Imagine yourself to be a teacher, right? An instructor, a professor. What would it actually require you, or what would be required of you to make sure that this chart is helpful in personalizing advice to the students? You understand? So please discuss that question with one another. You understand the question? The last question is about MS PhD students, which is also very important. So, but let's stick to the second question. Maybe you can discuss this also because they are connected questions, okay? So this is for any student and this is for MS PhD students, the last one. So you are interested with the task of, let us say, providing research inputs, advice to somebody. With this data, with the work of Professor Shikzen-Mihaly, okay, and his flow diagram, okay, as a tool, how could you possibly advise the students in a manner that they will do better? They will optimize their stay with you. You understand the question? Please discuss this. So these two are related questions. So kindly discuss with one another for about 2 minutes, and I will. You can imagine yourself, no? Put yourself in, let us say, my shoes or in somebody else's shoes and think about what it would be. Or you can talk about your own experience. I wish I knew this in such and such manner. If I were to teach somebody, or if I remember this student experience wherein if I was told this, I would have worked on this and that project would have been done. You know, all of us have misadventures with projects, right? We have had successes, but we have also had failures. So at some level, the explanation for that might plausibly come from a diagram like this. So I want you to talk about students in general. That could include things people like diploma students, polytechnic students, BTech students, BS students, BSc students, whatever. And then MS PhD students who are predominantly project driven, predominantly research driven. Okay. Malik, have I spelled Shikzen-Mihaly correctly? Can you just check? This is an interesting idea, no? You were able to put yourself in the shoes of a teacher? It's like, I don't want to do that ever. Yeah, that is correct. He was not Czech, he's Hungarian, yeah. Okay. Sorry, correction, it was not a Czech scientist, it was a Hungarian scientist. Yeah, why don't you discuss with one another? You have decided not to talk to one another, is it? Naveen and Varada? Discuss. Okay, what did you discuss? So basically start from where they are, find out where they are, give books if necessary, maybe even laboratory experience if necessary, maybe some simple experiments to begin with so that they upskill themselves. Okay. What about you?
So, if I am a teacher, what I will do, there are two kinds of approach. One is you define the problem, or you ask your student to define the problem.
Or you can do a combination.
Yeah. So, you first fix like a challenge level first. So, if you define the problem, you can explain what is the challenge level, what kind of skills it is. Or if the student itself defines the problem, he knows what kind of skills he has. So, you will define a challenging set that will challenge him to learn more. Or the combination.
Yes, I feel a combination approach is better because there is a danger of the student being very conservative. Like, this is my skill level and maybe I should only promise so much. Okay. But if you say no, if you just learn a little bit more, then the level of the problem goes up and you will be upskilled and you will be able to solve a more interesting problem and so on. So maybe a hybrid approach that is very dialectic is helpful. So the student not necessarily getting a problem directly, or a student not necessarily getting problem directly. Okay, so there is no problem definition that is unilateral. That is either by the teacher or by the student, but they discuss and sort of come up, and you also get a handle for where the student is and sort of say, see, I know you can do this, but do this, and for that read ABC and study ABC, do such and such experiments, and so on, right? So that seems to be reasonable. Bodhi? Correct. So their skill sets will be very, very different across the classroom.
Challenge that may be
Some mix is required. So even in the classroom, you need to have a mix of questions, you know, some that everybody can answer if they have sort of at least. Oh, you want to have a diagnostic test in your class so that you know what the spectrum is. So that is a very interesting approach. So you'd run a diagnostic test and then say, look here, those of you who have gotten a score of A to B, you know, read up XYZ. Those who have gotten a score of B to D, read up 2, 3, 4, you know, and those who have gotten a skill set, or those who have gotten a score of, let's say, E or F, you please, in addition to that, revamp or recap your dash experiment or something like that, you know. So that kind of a prescription you are saying, you know, right? That's a very clever idea actually. So there are some fantastic ideas that have come off this class. One is, you know, sort of collaborative discussions and collaborative problem definition. Even before you start problem solving, let the collaboration begin during problem definition itself. So between the teacher and the student, right? So that the teacher basically pegs it sufficiently high but not too low, and the student doesn't peg it too low or any such. So the idea should be to make sure that the teacher's responsibility is to peg it slightly higher so that there is sufficient upskilling possibility, and the student's participation's role is to make sure that it doesn't sort of result in anxiety. It doesn't necessarily go out of their entire ken, right? So that is one very interesting idea. And then you gave a suggestion on, yeah, so see where the student is and progressively, sort of progressive definition of problems that require higher and higher level of challenge so that they are on a continuous path of growth. That is very nice. And he's talked about diagnostic test and sort of giving a prescription based on the diagnostic test. So the diagnostic test need not be a part of the graded set of problems or any such thing, but you say, okay, if you have, and you could also do self-evaluation. You can say, okay, these are the responses to the questions that are correct or ideal, and based on that give yourself a score, and if your score is this to this, this to this or something like that, then, or it could be peer evaluation also. So they could sit together, pass the sheet around, and one could evaluate the other ones and so on, and then you could create a recommendation mechanism, right? That would be very interesting. Malik? So both of you think that the diagnostic test will be very helpful. What about for MS PhD students? For that, what you said is very relevant, isn't it? Collaborative problem definition, because then the student sort of has an opportunity to say, okay, this is my skill level, and so this is in my control, this will be a challenge. And then you can say, okay, why don't you divide this problem into that which is in control and that which basically puts you in flow, and then you progressively move in that direction, correct? So identifying the elements of a project, identifying the elements of the student skill set, of the problem that is at hand and the skill sets that are required to solve the problem will be very handy in project management, right? Time management for the student, education management for the student, and so on. So I find this a tremendously powerful tool. I use this very often when I advise students, for instance. I do not explicitly talk about it, but I think I have benefited a great deal from roughly ideas that come from this pool of general concepts that we have discussed. Okay. The next class will be about special education, which is increasingly important not just in school but also in colleges and universities, but we will not talk about that right now. So we will come back to content as of now. So how many minutes into the class are we here? So we will start with just one thing, okay, and we will stop and we'll take off from there, alright. So let us look at this chart now. Yeah, this is a very important chart. It's also a little bit like your phase diagram because you have two parameters. On the y-axis you have the degree of crystallinity, and on the x-axis you have the weight associated with the polymer. So notice that if it is very liquidy, greasy, do you expect a high crystallinity? Certainly not. You don't expect high crystallinity because it's flowing, it's a liquid, it's grease, right? And on the other hand, notice that there is a curve that looks like this. It's almost saturated here. This, on the other hand, looks like this. This is fascinating, right? And then notice that there is a difference here. This is called the brittle wax and this is called the tough wax. What is toughness? The amount of energy that you can put into the material before it comes apart. So this is interesting because when you, let us say, are at this point, this is brittle and it becomes tough when you go down. That means when you improve the crystallinity, what is happening? The toughness is improving, is it? Or when you, reduce the crystallinity, what is happening? Toughness is increasing. Now in light of what we saw as far as crystalline domains are concerned and amorphous regions are concerned, etc., give me a plausible explanation for this. A student-driven plausible explanation for this. Why is it that when I drop from here, go down in percentage crystallinity, I go from a brittle wax to a tough wax? So most of the candle waxes, for instance, are brittle. You can hold a candle, it will come apart, right? But interestingly, there is a mechanism by which you can make it tough. This is fascinating because this would mean that those candles can be stored very easily, transported very, very easily, correct? If they are tough, they are not brittle. So typically candles break, you know that, right? It's very difficult to transport them. But here you have an idea. This is an interesting idea. Did you notice this? So all the waxes typically have this molecular weight. There are a few kilodaltons. Alright, there are typically a few kilodaltons. So all the waxes, including the wax that you see in a candle, fall in this range. So typically from 1 kilodalton to about 10,000 kilodalton, 1 kDa to 10 kDa, that's about what waxes look like. But notice this. And this is even interesting. Now, I can actually have something like this and reduce the molecular weight. What would happen? It would become soft. So, brittle, tough, soft. So, let us discuss this part for now. Okay. So, turn to one another and discuss this. You've discussed. You're welcome to use your data also if you want. You can open up data, improve the quality of your explanation. So, you might have one level of explanation right now. Open up data, look for more data. Okay. And see if you can get some examples for this. So, why don't you open up your data devices and improve the quality of your explanation. Wherever you are, see if you can actually notch up the explanation by at least one level by using a little bit more of data that is coming out from your research and so on. You understand the question? So, you have some explanation now. You all seem very confident, okay, which is nice. But let us notch up the explanation a wee bit. Maybe you can come up with a cartoon for what might be happening, because I am looking for this explanation, you know, brittle, tough, soft. This triangle is what I am looking for. And soft is particularly interesting because you see soft here, right? And then you see soft here. And then between the two, so you see soft here. So you see soft here, this is a two-dimensional region. You see soft here. So, and you can discuss with one another. Whatever data you are getting, please discuss with one another. So, progress made? Yes. What's your explanation? Very nice. Why don't you go to the board? You can erase that right side. Make a cartoon. This part you can erase. And that's a very helpful cartoon actually. I'm glad you stumbled upon it, and let's use that cartoon to explain this, okay, this triangle, brittle, tough, soft. Yeah, we can stay with this. This is good, very good. This is a very good cartoon, and let us start with what you think is happening. So clearly he has shown the crystalline parts and amorphous parts, and now the question is, what will happen if you increase the amorphous part? What will happen if you increase the crystalline part? And what will happen if you shrink the lengths of the chain? Because that would be what would happen if you reduce the molecular weight, right? So there are three things that you have to discuss. Yes. I'll stand close to you so that you are heard.
If we increase the crystallite phase, like there is 100%, it is brittle because means the crack propagation will be easy. But in the case of amorphous, if you take these amorphous region will absorb the before it fractures, the energy which is absorbed, that's what called toughness. So if you increase these like amorphous region rather than this crystallite region, we can get tough polymers rather than brittle polymers.
So what he's saying is that there is value to increasing this part. Is that consistent with what we are seeing here? So yes, so where does molecular weight, for that matter, essentially the length of the chain come into picture? Yes. So what will happen if you shrank this, and so on? Do you expect it to become softer, stiffer? Essentially Young's modulus. Do you expect it to be softer or stiffer? I'm going to shrink this a little. You think it will be stiffer. How does that correlate with what is given here? So I am freezing the crystallinity. So basically what I am going to do is, I am going to have exactly the same situation, but I am going to divide this long chain into two small amorphous chains. So I will actually have fluffier chains. I will have fluffier chains, so it becomes softer. That is what is actually happening. See? Yeah. So that is an important point, because let's say I have brittle wax and I started out this problem with the candle transportation problem, right? And the question was, what solution can you give to the candle makers so that they are able to transport with lesser loss? After all, lesser loss of candles would mean more income for them. So first solution is, of course, make it more amorphous. Okay, make it more amorphous. For instance, they might be giving it a lot of time to cool. So if they can do more rapid cooling, then it would become softer. And then another thing is, they could start with a material wherein you have slightly larger molecular weight than what they already have right now. Okay, then they would be operating in this region and it would be tough. So we have solved a very interesting problem for candle makers. Correct? Very nice, no? Very, very interesting. So this was a design problem, by the way. Okay. So you can make a difference to candle makers. And by the way, Chennai has a lot of candle makers. So I am very sure that they do not know this. A large number of candle makers wouldn't know this. So you can make a difference. You can look at the process and say, okay, how can I make sure that the candles that they have are more easily transportable, are more easily transported? And the answer to that lies in a very interesting material science related fact, right? Now let us look at another thing. So as you increase the crystallinity, of course, it becomes progressively hard, and there is no surprise there, correct? As you increase the crystallinity, at any given point of time, let's say I am here, I am basically having this crystallinity versus this crystallinity, this harder. You can see that, it's very clear, right? So at any given point, if I make it progressively crystalline, it becomes harder. It doesn't necessarily become tough. For it to be tougher, so it's hard. For it to be tougher, I need to sort of tone down the crystallinity a little bit. Okay. So based on the situation at hand, you can design a solution for the problem. So with this, we will come to the end of this class. So why don't you spend 2 minutes making a knowledge tree? So pedagogy knowledge tree and content knowledge tree. You can integrate what we studied today in polymers with what you studied yesterday also. That is also welcome. Okay, just 2 minutes, not more than that. Discuss with one another. So that is the tree diagram exercise, and with that we come to the end. Very good. So brittle, tough, ductile, soft, and the fact that some of them are greases, right? So you have greasy materials, grease and liquids. Yeah, because see, whenever you give a lot of time for cooling, there is always a possibility of crystallinity, because crystallinity requires this neat folding. Yeah. So if you on the other hand rapidly cool, the amount of amorphous region will increase. So you could play with the heating rate, or cooling rate of the candles when candle is being made, and that would make it more easy to transport in principle. So you could just play with the kinetics and that would solve the problem. Very fascinating, no? Very fascinating, right? So you could go to a candle making factory and make a difference right now. So hopefully you will make many such charts for yourself. We will call it the Malik's charts for wax processing, and you can make a difference. You can go on to set up your own company. Yeah, that would be lovely. Alright, so you continue making the knowledge tree. I will wind up the class because we are almost past the time. So let me summarize, and in the next class we will begin with your knowledge tree. So there will be some continuation. So to summarize, we looked at a recap of various pedagogical ideas, but we also looked at flow, and in fact the students came up with some fantastic ideas on how flow can be actually used for teacher-learner interaction. And in fact the primary idea was conveyed rather quickly to all of them. They looked at the Mihali's flow diagram, and the Mihali's flow diagram sort of indicated to them that there may be a more design-oriented approach to teaching learning. Number one, that which requires some calibration of where the student is. Number two, that which requires some collaboration between the teacher and the taught, both in terms of problems as well as in terms of project definitions, right? And at the same time, this constant iteration, so that the student basically progressively moves up the skill scale. Alright, so most people understood this, and we also discussed student development and the three nearly axiomatic foundations for student development. Then I asked the students to sort of think about this, a very interesting data, and we used it to solve a problem that obviously exists in the candle making industry, that of a transport problem. A large number of candles basically get impacted and then break during transportation, and the question was, can I use this graph, this chart? And by the way, now there are slightly more evolved charts that are available, and if I were to think that Malik follows up with this, we will also have a set of charts called Malik's charts, you know, somewhere like this. And it turns out that you can come up with a very interesting, rather interesting approach to solving the transport problem associated with breaking of candles, because they break because they are brittle, but you can play with crystallinity, which means you can play with the kinetics of solidification, or you can play with molecular weight. But kinetics of solidification is the easiest to play with, and as a consequence, what you are doing is you are actually increasing the amorphous region and making it more tough, okay, and that would by and large solve the problem. And that was the design problem, and the students are currently working on the tree diagram. Here is where we will start, okay, and with that we will close this session on of this course, and I'll see you all very soon in the next session. Thank you.